kind of work did you do?
It's not protection when it's actually executing, but it's the protection when it's.
I'm sorry?
It's the work that I did was not about the protection when the program is actually executing on the FPGA, but it's when it's being stored and when the FPGA is being configured. At those two.
I see.
Does that mean it's stored encrypted in some way, or?
Yeah, it's stored in an encrypted way, but so when you connect, so typically it will be stored in some kind of a flash memory on the board. So when you read, when you put up your FPGA, so it will be read from there by the chip, by the FPGA. So at that time you have an interface that needs to be protected. But once you get inside the FPGA, there's other ways of authenticating also, which I did actually in this particular case, that this bit stream is not something that have been tampered with. So there's an authentication module there that authenticates bit stream based on some key exchanges, and then finally the fabric is programmed.
Okay.
But of course,
but if it's by encryption, then basically you just do it, right? You just encrypt and then sign the thing.
Yeah, but I mean there are obviously issues in what kind of encryption to use and what is the speed and how it's going to affect the performance. Once you put up your PC, your design, how much time it takes for all of these things to happen.
It's not possible to download the bits from the FPGA after they've been stored in the YouTube over
From the FPGA, no. It's very difficult to download a bit stream from the FPGA, because on FPGA the bit stream is not generally stored. The bit stream basically programs the connections between different elements on the FPGA. So it's like a programmable chip. So it's stored somewhere outside the.
The basic program build that is just code in the IoT, right?
Yeah.
So there's no way I can take the FPGA like out and just read off the IoT, so.
Okay. Some people have tried to do that. That they can take the FPGA out and try to see how it has been configured, but it's very difficult. I mean, they did achieve some results, but it was on a very small scale for simple designs. And it takes a lot of effort. So unless you are really motivated to do that, you would not be doing it.
Right. You're saying
of course, you also have side channel attacks and other ways of extracting that kind of information. So when your design is actually executing on the FPGA, you can do a differential power analysis and things like that. Right? Unless and until somebody is really motivated to do that kind of work.
like let's say I was, I had unlimited money and I hired you. How long would it take you to extract the bits in some usable form?
Okay.
For someone else's design, not so your own design.
Okay. I would say that would take, say, maybe if I'm not aware of how complex the design actually is within the FPGA. So like FPGAs vary in sizes, and the biggest ones can accommodate like millions of millions of transistors. So if I don't know how big actually the design within this thing is, and I just want to extract some information, which may or may not make any sense,
right,
then that would take like 2 to 3 weeks.
But
whether that will work or not, that's another question. I mean, you get some bits of information, but what does that mean in the entire picture? So unless you are able to get that entire design out of it.
So what you're saying, you can't extract every bit and every reprogram it yourself?
But when you do, so when you're trying to do it, you also have to understand that if say I'm using a differential power analysis to do that, so design must be executing on the chip. Now for the design to execute as it was intended to execute, I should be able to feed it the right set of inputs.
Right.
Otherwise I'll get something which won't make any sense. So
for an technical, this market definitely would motivate you to spend a few weeks and then do this stuff. Right? Why would you not be motivated?
Because even if you do a differential power analysis, you will not get, because you have to know the entire system to get the entire information out of it. So unless you know what the design intends to do, or you are able to figure out what kind of design is implemented within it, or which is the biggest system within which this design fits.
So FPGAs don't have JTAG or something like that?
Sorry?
FPGAs don't have JTAG?
FPGAs, typically FPGA won't give you JTAG access. So unless you implement a JTAG chain yourself in your material design, the FPGA won't give you JTAG access except for programming. So those lines are reserved for programming, not for you scan the device and see what is there. But say if I have done a design,
impose as a programmer.
of course. If I say I have done a design which I think might be stolen or theft can occur, I would probably remove the JTAG in the production system.
So when you buy the chip from Xilinx, does the chip from Xilinx come with JTAG or not?
The chip itself?
Yeah.
No,
So here's what I imagine, right? I take that, I keep power and ground, I take off all of this disconnected,
Yeah.
I pick that up, put it in my
Okay.
little socket, and then my exist socket, and I basically just read out and I have access to JTAG, and I can do whatever I want.
The chip from Xilinx, the JTAG is there, but it's not accessible in the sense like it's only there meant for the programming of the chip. So in the production chips that they release, it's not connected to the logic on the chip. So whatever digital design that you do on your FPGA, that has no connection with the JTAG.
I guess I'm a bit confused because I thought the whole purpose of JTAG so was that they could test the chip for the main purpose before selling it.
Yes.
It seems like you ought to be able to read and write to every.
Yeah, so before you sell the chip, you can do that, but once you move into the production system, once your chips are not in the engineering sample state but in the production state, you can disable those features from the chip. You don't need to have those. So, should I move?
Yeah, go ahead.
Okay, so in this part of the talk, I'll basically present some early ideas that I have been working on in my part-time because I have an interest in these kind of systems, or hardware aspects of these kind of systems. And I'll also talk about what research in this space means to me. So there will be different parts other than the hardware. So if you're looking at research for critical infrastructure systems, what kind of research probably excites me more? So I would say research that gives you actionable insight. Now, what does actionable insight mean? Every research gives you some insight, it gives you some information, but can you act based on that piece of information? Can it give you something else? Can it scale up to some other processes and connect with some other processes, the part of which is this small problem that you are trying to address using your research? So that is what I call actionable insight. Now, for critical infrastructure systems, these are high reliability and safety critical systems. So whatever work we do should also make business sense and should fit in the workflow with minimal deviation unless absolutely necessary. Because no matter what we do, unless it makes these kind of senses, it's unlikely that it will be adopted. So the idea is we solve a piece of the puzzle, but we should see the bigger picture also.
So can I ask maybe a retroactive question?
Sure.
What was the actionable insight you got from your PhD work?
Okay. For my PhD work, my focus was more on improving the HLS methodology. So now I can say that if I take what I have done and put it in a tool flow, in a high-level synthesis tool flow, I'm sure we'll get better results. And the results will match with what a hardware designer do. And the reason why I can say that with some confidence is because I had a chat with the video IP systems director at Xilinx, and he was very interested in this kind of methodology for video IP integration using HLS, because his customers wanted to use HLS but they were not able to use it because they would say, I would just throw a H.264 coder or decoder C code on the flow, will it work? And then he would say, obviously it won't work because it's not supposed to work like that. So
Yeah, please, go ahead.
So resiliency has been a major field of study in different other aspects of engineering also. So you have the banking systems, where a lot of effort has been spent on making them secure, their communications, their infrastructure, everything, and you have the relevant NIST guidelines on those. In the medical field, you have the FDA guidelines on how to make your medical devices, especially those that make use of electronics and electrical components and mechanical components, resilient so that they don't fail, because these are very critical systems. In the aviation sector also, you have similar work that has been done, and you have some standards like DO 178 and 254 for software and hardware respectively to ensure that these kind of systems don't fail or they're able to survive. And then there's within the transportation sector again, you have the railway safety and reliability aspects. So you have groups like I3P, which is actually in US itself, working on the SCADA systems related to these SCADA and other aspects of this kind of transportation structure. So what should be the guiding principle for this kind of research? I don't think attacks can be prevented. They will happen. But what can we do? We can frustrate the attacker. And why do we want to do that? I mean other things. Because the more persistent an attacker is, you have a better idea of who the attacker can be. And then there are three parts here. So we have information, knowledge and wisdom. So whatever work we do, we get a lot of information. But that information should be converted into something which would be knowledge. So if I'm aware of these things, can I act upon it? And finally, that piece of knowledge will give us some wisdom, which is basically an insight into looking at the context and other aspects of the activities that we have been monitoring or looking at. Since I come from a hardware background, and I have done most of my work on hardware, I'll first talk about device level resiliency, which is also mentioned in NIST guideline on cyber security for critical grid systems. So what kind of devices you have? You have smart meters, which record your consumption. You have aggregators, which record the data from different smart meters. You have programmable logic controllers, which control the different mechanical or other equipments on the grid. And you have the servers, which store your data. So one of the ideas that I had been working on for some time on my own was, can verification vectors act as security guards? So when you design a chip or a piece of hardware, you spend a lot of time verifying it, and you spend a lot of effort and money. But once that chip goes into production, all that effort that has been done beforehand remains with the guys or the team that has done it. But can that kind of information be used to protect the compute and the communication logic in your chip? Of course, it will have an impact on area performance and other aspects of your design, but can it be used? So this is a question that I've been looking at.
These would be verifications that would be for the specific design or the correctness of the chip? Or both?
It could be, okay, so typically in verification you verify the functionality of your design. So if you have a compute and communication logic, you have a set of vectors for which it will work. So what will happen if you give something that it was not supposed to be fed? So if you give an input which has not been tested or which was not part of that framework, how will this thing behave? So that's one way of breaking down your system. So the effort that has gone into verifying this logic using, say, test vectors and other methods, can that effort be consolidated and used as a security barrier on the chip itself?
That's to detect tampering or to prevent tampering?
Well, to prevent tamper, you still have to, I guess, detect tamper a little bit. So what we do with that depends on you. I mean, that's a design consideration that you make, whether you just want to detect or prevent, or do both of those. Because that will obviously have an impact on other aspects of your design in terms of performance.
So is there a pathway to implement this idea into a normal device? Like here you're suggesting, why don't we build in the security into the device design, the hardware, right? Now that's, I think is a reasonable idea, right? Good idea. But nevertheless, practically we're faced with the fact that basically we just buy the devices, right? So is there a way to somehow retrofit this technology in the COP devices? What do you think?
I think retrofitting can also be done because if say one way to do this is to do pattern matching of your verification vectors. So whatever comes as input, does this belong to the set of vectors that I've used to verify my design? So that if say that is one way, I'm just saying that is one way of doing it. Can that be done on an external piece of hardware that you can just plug in? Of course,
that's the question.
Yes, can do it.
Can do it.
Yeah.
But you'd have to know, right? You have to know the internals to develop proper verification vectors.
So, okay, yes. I mean, if you are trying to do a retrofit, you can't do it on a black box, which means the device, you should know something about the device, so what kind of functionality it has, what kind of inputs it expects. Only then you can do this thing. But I think that kind of information is generally available, so you are at least aware of what kind of protocols are there, what kind of inputs are coming to or are expected to come on to the device.
Is there any related research in this area? Because it's obviously a high impact area if someone succeeds in doing this, right? So I assume that
Okay.
what's been done and what do we know and so on.
Okay. Most of the research work on security has focused on exploiting vulnerabilities in a design, which can be fixed using software, or you exploit it in hardware and tell the guy or the company which does this hardware design that in the next release you try to take care of it.
Yes. So that's the problem, right? So you identify the problem, right? You know there's this existing chip design, it has this problem.
Yeah.
Now you're saying I can add on the chip to the existing device and somehow make it resilient.
Yeah.
I would love that idea, right? I would immediately go buy it if I have a mission critical infrastructure to run.
Yeah.
So what kind of research has been done?
I have not come across a lot of work that has been done like that. I have come across some work in the industry where people have, and that was I think long time ago, 4 or 5 years ago when I saw a presentation, in which if you try to physically extract information from the board, so they had this small piece of hardware that would basically destroy the entire board. So that was not more like protection, that was more like prevention. So if somebody is trying to make an unauthorized access using some of the ports.
No, but that port was specifically designed to have that property, right? Instead of a retrofitting.
Yeah.
Instead of an add-on.
Yeah.
So add-on basically is a brand new area.
Yeah.
Just look at the verification, like say when you're verifying an FPGA design, you actually do you take up some of the LUTs for the verification hardware and
No.
code, or is it all just you basically just pump
Okay.
external inputs and outputs into the chip? And
Okay. There are three steps in verifying design of FPGA. One is you start off with the RTL design, which is just the design, and then you verify. You do its functional verification. So you have a suite of vectors, a test bench, or in a verification environment, and you see if this design can functionally work properly.
that's
There are-
software simulation?
Yeah, that's the software simulation.
Yeah.
Thereafter, once you have mapped your design on the FPGA, there's another two kinds of verification that you do. One is functional and the other one is timing. And in this particular case, the tool will give you a model. So the model is actually a physical model of the design as it has been implemented on the chip. So the functional verification would actually not take into consideration the timing on the chip. So it will just verify whether the mapping has been correct.
So is the bits in, the bits out are what you expect
Yeah,
to see or whatever.
Yeah.
Right.
Then the next step in verification is to enable that timing information in a verification environment.